Good evening, ladies and gentlemen, or good afternoon, ladies and gentlemen. You're in for a special treat this afternoon as you can look at all the props that we have here. We're moving away from PowerPoint presentations toward live scientific experiments. So welcome to Sturgis Hall in the Clinton School. My name is Skip Rutherford. I'm Dean of the school. And I would ask that you please turn your cell phones, your Blackberries, and other electronic devices off if you would right now. To introduce our program today is a Clinton School staffer whose fingerprints can be found on every public program we have hosted. Nikolai DePippa is the Deputy Director of Public Programs and works closely with Patrick Kennedy to bring to Arkansas one of the nation's best and most diverse and most unique speaker series. And I encourage you to read this morning's style section in the Arkansas Democrat-Gazette about our speaker series. For almost every guest who comes to the Clinton School, Nikolai is working with that guest and his staff, or her staff, and he is communicating with each of you, all of you who are attending these events. Everybody responds to Nikolai with their emails. A graduate of Hendrix College, where he majored in biology, so he has some understanding of what we're doing today. He was also captain of the varsity soccer team. He shares two things with our speaker: a passion for science and an Italian heritage. Ladies and gentlemen, Nikolai DePippa.
I had notes for this, but I didn't know this was going to be on the podium, so I'm going to have to do this without them. As Skip alluded to, I do have two things in common with Dr. Phillips. The Italian heritage can be traced back to Wilkes-Barre, Pennsylvania, which is where my father was also born, and I'll be there in 2 weeks for a wedding. The love for science has been with me, as well as Dr. Phillips, our entire lives. I now am the Deputy Director of Public Programs at the Clinton School. He's a world-renowned scientist. I'll let you know how that goes after this. He graduated from MIT in 1976. His thesis centered on, this is going to be the hard part, laser cooling, atoms, trapping protons, and that is the main thing that he is known for. What good does science have for the common man? As the paper stated this morning, and many of you know, one of the goals of the public programs is to show all avenues of public service, especially the ones that go unseen. And I can't think of anyone better than Dr. Phillips to explain this. And he did win a Nobel Prize in physics in 1976. So without further ado, please welcome Dr. Phillips.
Well, thank you. Thank you very much. It's a pleasure to be here, and a pleasure to be here at the Clinton School of Public Service. Public service is something I believe in very much. I work for the U.S. government. I work for the National Institute of Standards and Technology in Gaithersburg, Maryland, and we're part of the Department of Commerce. We get support from not just the Department of Commerce, NIST, but from a lot of other agencies, the Office of Naval Research, the Disruptive Technologies Office, NASA, and we're in a partnership with the University of Maryland in a thing called the Joint Quantum Institute, which is also supported by the Laboratory for Physical Sciences, which is an operation of the National Security Agency. Well, what do we do at NIST? Well, we do a lot of things, but one of the things that we do at NIST is take care of the standards for measurement for the nation. If you want to know how long something is, that's our job. If you want to know what the mass of something is, that's our job. If you want to know how long a second is or what time it is, that's our job too. And what I'm going to be telling you about is things that relate to the measurement of time. And it's been our job since we were formed to have really good clocks and to be able to disseminate the standard of time. So when people measure time, they know what they're doing. Now you might ask, how well can you measure time? Well, for less than $100, you can buy a quartz watch. Many of you probably are wearing one. And if that quartz watch is any good, it probably is accurate to about a part in a million, which would be about 30 seconds in a year. Now, if you're willing to spend a little more money, say $100,000, you can get an atomic clock that is good to a part in 10 to the 12, or a part in a million. Now, in fact, I think that's quite a bargain. You spend only 1,000 times more money and you get 1,000,000 times better performance. But some people might wonder, who really needs to have time measured that well? That is, what are we spending the taxpayers' money for, measuring time to that degree of accuracy? Most of us probably think that we don't need to know what time it is to that level of precision. But the fact of the matter is that you do need to know what time it is to that level of precision for many of the things that are part of our modern technological lives. I'm sure that a lot of you have seen global positioning system receivers. You may even have them in your cars. You might have taken them backpacking so you don't get lost. These global positioning system receivers work because there is a constellation of satellites, 24 satellites orbiting the Earth, each of which has on board several atomic clocks. The atoms in these atomic clocks act as the tickers, just like the quartz crystal in your watch is the ticker for your quartz crystal, and the pendulum in a grandfather's clock is the ticker for that sort of a clock. The atoms are the tickers in an atomic clock, and atoms make the very best tickers because all atoms of the same kind are absolutely identical with all other atoms of that same kind. We define what we mean by a second to be a certain number of ticks of a certain kind of atom, cesium-133. And every cesium-133 in the entire universe is absolutely identical as far as we can tell. And so we use these atoms as the tickers for our clocks. And at NIST, we've always been trying to make these clocks better and better. Navigation is one of the reasons. The global positioning system allows you to navigate anywhere on the face of the Earth where you can see 4 of these satellites. You can determine your position to within a few meters. Scientific research demands very accurate timekeeping. Other things having to do with national security, one of the reasons why we get money from the National Security Agency is because the things that we do impact national security as well. But there's one of the things that I'd like to emphasize. At the beginning of my talk, I had a subtitle under science and public service, and that was Time, Einstein, and the Coolest Stuff in the Universe. What does Einstein have to do with it? Well, as it turns out, many things. And I'm not going to tell you all the things that Einstein has to do with what I'm talking about today, but one of them does relate to the global positioning system. In about 1915, Einstein came up with a theory of gravity, a new theory of gravity that replaced Isaac Newton's theory of gravity, which was only an approximation to what we now believe is the correct understanding of gravity. This theory of gravity is called general relativity. And when it first came out, the newspapers reported that this theory was so complex that only 3 people in the world understood it. Today, if the engineers who built the global positioning system had not taken into account the effects that Einstein predicted in his 1915 theory of general relativity, if they had not taken into account those effects, the global positioning system would be in error by kilometers, and it's accurate to meters on the fly and to centimeters if you're willing to sit around and take data for a while. And it would be wrong by kilometers if they didn't take into account general relativity. I have a friend who once went to one of these big shopping malls and parked his car in a parking lot with another 10,000 other cars, went in and shopped for a few hours, came out and had no idea where he'd parked his car. But because he had his handheld global positioning system receiver, he could walk back to his car. So a theory that in 1915 was so arcane that supposedly only 3 people in the world understood it. Today, you need that theory in order to find your car in a parking lot. This is the way things often happen with science. But you might ask, what do these atomic clocks look like? Well, I once found this advertisement in a magazine. It says quite correctly that scientists in Braunschweig, Germany, Braunschweig is the home of the German sister institution to the National Institute of Standards and Technology, that they had set their atomic clocks back 1 full second, and this airline company says, we've adjusted our schedules accordingly. Right. The thing I want to point out, though, is that the instrument in front of which these 2 dorks are standing does not look anything like an atomic clock. In fact, if you were to go to our laboratories in Boulder, to our atomic clock laboratories, you laugh. But this is what the atomic clock actually looks like. And inside that long tube that you're looking at here, inside this long tube, there is a stream of atoms going along. And that stream of atoms are the tickers for the atomic clock. Now, where do those atoms come from? They come from a gas. We take some cesium metal, we put it in a can, we heat it up so that it vaporizes and it makes a gas, and those gas atoms are moving around at about 200 meters per second. Some of them come out through a hole in the side of the can and they make that atomic beam. Now, the problem with atomic clocks is that they work really, really great, and in fact, the best of them that are made according to the design that you saw in that cartoon right there, the ones that look like that, are as good as a part in 10 to the 14, as good as a part in 100 million million. But we are always trying to make clocks better and better for all the reasons that I mentioned. And we cannot make them better than that. Why? Because the atoms are moving so fast. There are a lot of reasons why that fast motion makes it difficult to make a better clock. But one of them is extremely simple. The atoms are moving so fast, they don't stay around in our apparatus for very long. And if you can't look at something for a very long time, it's hard to make accurate measurements on it. So that's one of the main reasons why these atomic clocks cannot be made any better than this fantastically accurate part in 10 to the 14 that we achieve. But we want to do better. That's our job, is to make clocks that are better and better, because people are constantly demanding higher and higher accuracy from these clocks. But we can't because the atoms are moving so fast. Let's talk about temperature now. The difference between hot and cold is the difference between fast and slow. If I have a gas of atoms, like the air in this room, and it's hot, and actually it feels kind of warm in here, it means, to say that the gas is hot means that the atoms and molecules are moving around really fast. The nitrogen molecules in the air in this room are moving at about 300 meters per second, about the speed of sound. No accident, by the way. And if you cool down the gas, then it means that the atoms and molecules are moving more slowly. So if we want to make better clocks, we want to make the atoms that we use in those clocks move more slowly. That means we have to cool down the gas. And if we're going to cool down a gas, we want to cool it a lot. And so to give you an idea of the kind of low temperatures we're going to try to achieve, I brought along some really cold stuff. Inside this jug, this insulated jug, is liquid nitrogen. Now, nitrogen is the major constituent of the air. So that means this is basically liquid air. This stuff is so cold that compared to it, the floor on which I am standing is red hot, figuratively speaking. Imagine what would happen if you had a red hot stove and you poured cold water onto the red hot stove. The water would boil immediately, right? And that's what happens if I pour the liquid nitrogen onto the floor. It boils immediately. You see? This stuff is really, really cold. And so you might imagine that if you wanted to cool down a gas, then you might as well start with something that's really, really cold to refrigerate the gas. So here I have a traditional container for what we lovingly refer to in the Washington area as hot air. So I'm going to fill the balloon with hot air, which is in plentiful supply. And I'm going to put it into this bait bucket, which has been filled with liquid nitrogen to cool down the gas. So let me just stuff it into the bait bucket. And now let me just say a few words about how cold the liquid nitrogen is. Or perhaps maybe what I ought to do is to demonstrate a little bit just how cold the liquid nitrogen is. Here's a racquetball, nice bouncy racquetball. I'm going to dunk the racquetball into this container of liquid nitrogen, and we'll just let it cool down. While it is cooling down, let me do something else. Here's a rubber band, nice, flexible rubber band. I'm going to dunk the rubber band into the liquid nitrogen. Now, it's making the liquid nitrogen boil because the rubber band is so much hotter than the liquid nitrogen. But now, as it cools down a little bit, the boiling stops. That means the rubber band is down to the temperature of the liquid nitrogen. And if I take it out, it is frozen so hard that it breaks like it was a dry twig. But all I have to do is warm it up in my hands a little bit, and you see it's restored back to its nice, stretchy state. So you've got, I mean, this stuff is really, really cold. So you've got something that cold, then why not use it if you want to cool down a gas to make the atoms move more slowly? Well, most of the air, of course, is nitrogen molecules. There's some atoms of argon. But if we want to make the atoms and molecules move more slowly, then we want to use something really cold to cool down the gas. So let's see. Oh yeah, here, I don't want to forget this. Here's just an ordinary plastic water bottle. Some of you have copies of this, and you've been drinking water from them. What I'm going to do is I'm going to pour a little bit of liquid nitrogen into this water bottle through this funnel. I hope that I can see how much is going in. Okay, probably put more than I needed to in there, but that's all right. So I'm going to put the lid on really tight. Now imagine what would happen if you took a container of liquid and sealed it and put it into an oven. What do you think would happen if you had a container that you sealed and put into an oven? Well, the room here is like an oven, right? Because it's so much hotter than the liquid nitrogen. So we'll just see what happens. In the meantime, let's get the let's get the now you remember how nice and bouncy the racquetball was before. So now I'm going to try to bounce it on this concrete block. It breaks like it was made out of china. This stuff, my friends, is really, really cold. And you've got something that cold, then why not use it to cool down your gas to make the atoms move more slowly? So let's just cool down a little bit more hot air. What? I want to have lots of cold gas. Okay, so now one of the questions that I'd like to address is, I've shown you how cold this stuff is, but how cold is it really? Well, physicists like to measure our temperatures not on the Fahrenheit scale or on the Celsius scale, because that scale doesn't go down very far. You get down to 0 and it's still really hot by our standards. We like to measure things up from the coldest possible temperature you could have. Well, what is the coldest possible temperature that you could have? Well, hot means fast, cold means slow. What's the slowest you can go? The slowest you can go is stopped. And so if you're stopped, that's the lowest possible temperature. We call that absolute 0. It turns out things never actually stop. A little problem with quantum mechanics, but let's forget about that for the moment. There is a coldest possible temperature. It's called absolute 0. How cold is it? Well, on the absolute scale, where 0 is absolute 0, and room temperature is about 300 Kelvin, 300 Celsius degrees above absolute zero. That's what the room temperature is. Ice melts at about 273 on this scale. Dry ice, a pretty cold thing, 195 degrees on this scale. The coldest air temperature ever measured anywhere on the face of the Earth, someplace in Antarctica in the winter. And that, my friends, is why you never, ever put a closed container of liquid into an oven. Never, ever do that, okay? Because, as you can see, wow, you know, the way in which this thing exploded is really quite remarkable. I'm going to have it looks like it blew the top off instead of breaking the bottle. That's never happened before. That's really quite remarkable. Anyway, so coldest temperature anywhere on the face of the Earth, 185 degrees above absolute zero. This stuff, which is so cold that it boils when we pour it out on the ground, this stuff is 77 degrees above absolute zero. This stuff is really, really cold. And so you might think that if you've got something that cold, then why not use it to cool down your gas? But you will have noticed, perhaps, that some of you were astute enough to notice that the volume of the balloons that went into this container was, in fact, larger than the volume of the container. And the reason that was possible is that these balloons are flat as pancakes. Now, does anybody remember how many balloons I put in? 3? Well, there's one. Okay, there's another one. These things are frisbees. So there's the 3, right? 2 yellows and a blue, right? Now, how many of these kind of color balloons did I put in, or that color, or how many green ones did I put in? I don't know. Or whoa! That's wonderful, 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 wonderful. So as you notice, you see, except for the balloons that broke, these balloons are reinflating as they warm up. The air in these balloons did not go away. The air in these balloons condensed. And it turns out that if you take any gas and put it in a cold container in order to refrigerate it, and the container is cold enough, then the gas will condense and you won't have a gas anymore. And for making an atomic clock, you want the atoms to be in the gas phase because you want the atoms to be floating freely in the vacuum, as atoms do in a gas, instead of stuck onto something else. If they're stuck to something else, as happens in a liquid or a solid, then they won't tick at the same frequency. So we want to have the atoms floating freely in a gas. And what this experiment shows is that that's not possible if you cool things down in the usual way, because it will condense. So we have to find a way of cooling things down without touching them. And the answer to the problem of how do you cool things down without touching them, in a certain sense, has been staring at us from the heavens for centuries, because since the time of Kepler, people have known that the tails of comets point away from the sun. And one of the reasons for that is that the sunlight pushes on the dust and gas that make up the comet and pushes out the tail. So does the solar wind. But the point is that light pushes on stuff. And what we're going to do is we're going to use light to push on atoms in such a way as to make them slow down. And one of the reasons we're doing this is because it's the only way that we can get the atoms cold enough to be interesting without having them condense. But there's more than that. I mean, as cold as this liquid nitrogen is, or as any cryogenic liquids might be, I mean, 77 degrees. Unless you work in low temperature physics, this is the coldest stuff you've ever seen. I mean, it boils when I pour it out on the ground. This is fantastic stuff. The temperature is 77 degrees. The velocity goes like the square root of the temperature. That means that at 77 degrees, the velocity of the atoms is about a factor of 2 lower than it is at room temperature. That means that when the nitrogen molecules evaporate from this boiling liquid nitrogen, they're going half as fast as the nitrogen molecules in the air that are 300 meters per second. These things are half as fast at 150 meters per second. I've been working on this problem for more than 30 years, I did not get into this to make half-fast atoms. What I wanted to do was to make things that were really, really slow. So how are we going to do that? And the answer is we're going to use lasers, and we're going to shine the laser light on the atoms. And I'm not going to go into the details of how it works, but we selectively push on the atoms in such a way as to make them slow down. Here is a picture taken in my laboratory of a bunch of intersecting laser beams that are in a vacuum system. So you see, here's the laser beams intersecting like that, like this. And in the center is a ball of sodium atoms, about 1 centimeter across, containing about 100 million atoms in this case. And the question is, how cold are these atoms? How do you measure the temperature of these atoms? And the answer is, well, you don't just stick a thermometer in there. Well, you need to measure the temperature by seeing how fast the atoms are going. And we do that. We can measure how fast the atoms are going. Now, to give you an idea, let me give you one more point on this absolute temperature scale so you can appreciate how cold our atoms are. If you go into the outer reaches of outer space, space is bathed in radiation that is at a temperature of a little bit less than 3 degrees above absolute zero. It's the leftover remnant from the Big Bang. That's the coldest natural temperature you can get to in the universe, 3 degrees above absolute zero. With laser cooling, we were able to get down to a temperature of 700 nanodegrees above absolute zero. 700 billionths of a degree above absolute zero, 7/10 of 1 millionth of a degree above absolute zero, and more. There was a theory for how cold you could get, and we got 200 times colder than what the theory said was possible. That was really exciting. Now, one of the questions you might ask is, remember, I said we're doing this to make better clocks. What kind of a clock can we make out of this? Here's a picture of the new kind of clock that is in our clock laboratories out in Boulder, Colorado. This is Don Meekoff and Steve Jeffords, and they've made this clock. They laser cool the atoms down here. They shoot them up in this tube. And you see, the neat thing about this is that if you throw something up about 1 meter, it comes back down after about 1 second. So those same cesium atoms that in the traditional clock were going at 200 meters per second and lasting in the apparatus only a few milliseconds, now stay a full second in the apparatus. And these clocks, and ones like them in other laboratories around the world, are the very best timekeepers that have ever been made. The performance of these clocks is fractionally 4 parts in 10 to the 16. 4 times 10 to the minus 16 fractional uncertainty. That's 1 second in 80 million years. And they're getting better all the time. My friends, this is what we call close enough for government work. Now, these kinds of clocks are the standard for time and frequency for the nation, really for the entire world. They synchronize the GPS system. We don't have clocks like this orbiting the Earth, but these clocks on the ground synchronize all those clocks that are orbiting the Earth, and other kinds of clocks, not cesium clocks, which are the primary standards, but other sorts of clocks have recently been made in Boulder that are even better than this, using some of the techniques of laser cooling that we developed in Gaithersburg. And the clock making, which has a real impact on commercial and military applications, has been a very important application of our work. But we also do an awful lot of fundamental research, and one of the things we wanted to do was to get things even colder than we were able to do with laser cooling. Well, how do we get things even colder? It turns out it's a very simple idea called evaporative cooling. Now, you all know how evaporative cooling works. If you go swimming and you come out of the water and it's windy, you will feel cold. If your coffee is too hot, you blow on it and it cools down. What's happening is that the most energetic of the water molecules are escaping from the liquid water, and what's left behind is less energetic and therefore colder. We do exactly the same thing. We hold our atoms in a container, and we allow the most energetic of them to escape. The question is, what kind of a container can we hold our atoms in? We can't use a cold container because you saw that if you use a cold container, the atoms stick. Certainly can't use a hot container because it would heat the atoms up. So we have to use a container that is really no container at all, and that container is known as a magnetic bottle. And I'm just going to demonstrate for you live how we do that. This represents an atom. Our atoms are like little tiny magnets. In fact, they're like little tiny spinning magnets. This is a great big magnet, which is what we call our magnetic trap. And what I'm going to do is I'm going to spin this top so that it's just like our atom, and then I'm going to lift it to the place where the magnetic force cancels out the force of gravity so that this thing, if I've done everything correctly, will float. See? No strings attached. This is the real deal. So we hold our atoms in a magnetic trap, we allow the most energetic of the atoms to escape, and we end up with a gas that is as cold now, the record is less than 1/1000th of a degree above absolute zero. That's the kind of temperatures that we and our and colleagues elsewhere around the world have been able to get. But we've been doing that in the pursuit of basically trying to understand better how nature works. At first, we started off wanting to make better clocks, and now we're just trying to understand better how nature works. And this brings up a question that often arises when one asks how the support for scientific research should be parceled out, fundamental versus applied research. Why should the United States, either the government or the private sector, invest in research that simply advances knowledge rather than addressing societal problems? Well, there are a number of answers to that. In my own case, the work that we started out doing was directed to addressing a particular need. We needed better clocks, and so we wanted to cool down atoms in order to make better clocks. Well, at some point in that research, we had some things that we just couldn't understand. Everything was working really well. In fact, it was working too well. We had the atoms laser cooled in the way we thought we should, and we were going along on a path to make better clocks, but things just weren't adding up. And we decided that we should stop and make sure that we understood the process completely. Had we not done that, we would not have discovered how to get to temperatures 200 times lower than people had previously thought possible. And even though we didn't realize it at the time, if we hadn't been able to do that, we would not have been able to accomplish our mission. We would not have been able to make the kind of clocks that I showed you in that picture, where the atoms are tossed up and come back down after a second. That clock would not have worked had we not taken a digression in order to more fully understand what was going on and get both a theoretical understanding and an experimental understanding. Once we understood all those things, and only once we understood all those things, did it become possible for us to make the clocks that we intended to make. And along the way, we and other people made the discoveries that have led now to several Nobel Prizes for US government employees. Remember the story I told you about Einstein and the theory of gravity that he came up with in 1915? Nobody could have imagined that there would be an application for that theory of gravity. In fact, I'm sure that if you would have asked anybody at that time, can you possibly imagine any way we could ever use this for practical benefit? The answer would have been a resounding no. Today, the global positioning system is a multi-billion-dollar industry, and it only works because we understand how gravity works in the way that Einstein laid out in 1915. But that's not all. The very development of atomic clocks, the things that made possible the global positioning system in the first place, started from work that was done to study the properties of atomic nuclei back in the 1930s. And it led not only to the atomic clocks that make the global positioning system work, it led to things like magnetic resonance imaging, which is one of the mainstays of very careful diagnosis in modern medicine. And in 1930, no one would have imagined that that kind of work would lead to even atomic clocks, let alone that it would lead to medical imaging. And here's a really big one. At the beginning of the 20th century, people started to understand that the way in which microscopic and submicroscopic, really subatomic things behave, they do not behave in the way that macroscopic objects do. And for the first quarter of the 20th century, people were learning how subatomic stuff works. And that process, the description of how subatomic stuff works, is called quantum mechanics. And at the beginning of the 20th century, everyone would have said, well, this is really interesting from an intellectual point of view. It changes our way of thinking about things in a fundamental way. But this doesn't have anything to do with the way we build steam engines, the way we build bridges, and all that. Today, most of the things that we associate with modern life depend upon the fact that we understand quantum mechanics. This computer, television, this little clicker, the laser that I use to point at the thing, all of these things depend upon quantum mechanics. I have no idea how many billions of dollars of the gross national product, no, it's called the gross domestic product these days. Anyway, is accounted for by quantum mechanics, but a huge fraction. Nobody could have possibly imagined that that would have been the case back at the beginning of the 20th century. My point is that the most fundamental science, the science with no apparent societal benefit, has again and again had immensely important impacts on our society. Of course, science often works by saying, here's a problem, let's solve it. And it works very well that way. The Manhattan Project is perhaps one of the best examples of that. You have a goal, you put a bunch of smart people on it, and they do it. But far more often, the things that have been of the most benefit to our society started off because people were simply trying to understand better how nature works. Today, in the United States, the US government is almost the only entity that has the foresight to supply significant support for that kind of research. When I was young, there were industrial laboratories that did lots and lots of basic research. Today, none of those laboratories do basic research anymore. Only the US government supporting work in national laboratories like my own or in universities has what I call the foresight to do that. There is a really telling story that is told by Norm Augustine. You can't read it, it's too small. But Norm Augustine used to be the CEO of Martin Marietta, Lockheed Martin. And he tells a story about how when he was president, they came up with some fantastic idea for developing a new product that was just going to put them way above their competitors. They were so excited with this that they called a meeting of Wall Street investors to tell them about this new idea, how they were going to invest in this new thing, thinking that this would just turn on all these Wall Street investors. As soon as they finished the presentation, the investors ran out of the room, told their clients to sell Lockheed Martin, and the stock went down and didn't recover for over a year. And Norm Augustine went to these guys and said, "What's the deal?" And they said, "Our investors are interested in making money on a scale of a few months. We do not recommend investing in anybody who would be so short-sighted as to spend money on research that isn't going to pay off for years." Well, it used to be different in our country, and things have changed a lot. Investment in research is something that is incredibly important. Norm Augustine chaired a panel of people who wrote a report called Rising Above the Gathering Storm about the difficulties, really the crisis that our country faces because of the fact that we're not investing in research in the physical sciences. We've done very well in the biological sciences and the medical sciences, and not investing in the physical sciences, that we are putting our economy, our very existence as a strong nation in the world at risk because we're not investing enough. Well, people responded. The president responded, both houses of Congress responded, there was legislation passed, the American Competitiveness Initiative, the America Competes Act, are all responses to exactly this very important problem. But the legislation has not been funded. And today, U.S. science is in a crisis in many areas. We're not meeting our obligations that we agreed to with international partners for participating in international scientific endeavors. And we are finding that we are being outcompeted by European and Asian competitors. And the question is, what is to be done? Well, you people here at the Clinton School of Public Service may end up having an opportunity to influence this sort of thing. I don't know what's to be done, but I hope that you people can figure it out. It may lie exactly with you. But there's more than that. You're here at the Clinton School for Public Service. Public service is a very important part of our responsibilities as Americans. There are a lot more lucrative things you could do in your life than public service. And so one of the questions I pose to you is, why should you, students at the Clinton School of Public Service, go into public service instead of going into a career that will maximize how much money you can make? Well, people often have asked me that. I could make twice as much money if I went to a university, and I could probably make a whole lot more than that if I worked for private industry. So why am I still working for the U.S. government? Well, there are three reasons that I'd like to identify. There are a lot of things that are more important than money. And three of those that have kept me working for the government are the people, the work, and the service. Here is a picture of my research group at NIST. I have a core team of scientists who are permanent employees of NIST, who are among the best young researchers in America today. Besides that, we are blessed not only with the cream of the crop of young people getting their PhDs in the United States, but all over the world. So there are people in my group from Mexico, from South Korea, from France, from Italy, from Denmark, from Germany, and as well as wonderful people from universities all over the United States. It is a collection of people that really makes it both fruitful and exciting to do research. And I don't know anywhere else where I could have this kind of team of people. It is a popular misconception that government workers are lazy, incompetent clock watchers, watching the clock to see when they can leave on any given day and sort of treading water until they can retire. I don't know anybody like that. The people that I work with are staying late every night because they just can't tear themselves away from their work. They're coming in on weekends. They are trying to do whatever they can to get more out of the time that they have to work in our group. They're constantly thinking of new ways to do their job better and to take that job into new directions. And the work that we do together is just incredibly exciting. I already mentioned, why don't we show this picture instead? This is a picture of some of the data that we took that shows what the temperature of our atoms is as we change the detuning of the laser. And this is what the theory said should happen, that it should minimize right here and it should go up as we go to a bigger detuning. That means that the frequency of the laser changes. But in fact, we found that it was going down. And that was the clue that people needed to be able to understand what was really going on. A much more subtle way of cooling down atoms than anybody had anticipated was possible. And this is just such incredibly exciting work. I just can't imagine doing anything else. But a few years ago, I got an award for Service to America Medal for career achievement. And there were a lot of other people who got awards at that same time. And it was really awesome to see the things that these people did. Thomas Castelval, who works at the U.S. Geological Survey, he led a team of people who remapped New Orleans. You see, people were in their homes, on top of the roof, in the flood, calling on cell phones saying, I live at certain address. but there were no more street signs. There were only boats, and there was no way of knowing where to go. They remapped New Orleans into GPS coordinates so that people could find them using the GPS coordinates. And not only that, those members of the team went out in boats themselves to rescue the people. Mark Ward, USAID, he led the teams that responded to the tsunami and to the South Asia earthquake. He put together immediate aid packages that provided housing for 500,000 people and food support for 1 million people. These people are not clock watchers. These people are heroes. And it is an honor to work in the same government as these people do. Near my home, there is a little church, a little white church by the side of the road. If you go in the door to that church, there's a sign on the outside that says, "Enter to worship." When you leave that church, there is a sign on the inside of the door that says, "Depart to serve." Service is what it's all about. I believe that is why we are here, to serve others. And by serving others, to serve our country, and by serving our country, to serve all of humankind. And so, not everybody is going to be somebody who rescues Katrina victims from the roofs of their houses after having reprogrammed the map of New Orleans. Not everybody is going to be able to save 1 million people from starvation. Not everybody is going to be able to learn new things about the world works so that we have better clocks and better navigation and better national security. But each one of you has a way in which you can serve your country, your fellow human beings, and the world that you live in. And whether you are in formal public service working for the government, or whether you are in the private sector, there is a way in which you can serve, and I challenge you to do that. Thank you very much.
We've been blowing bottles up all morning, and this is what happens on the first one, and this is the one that he did.
So sometimes results aren't always predictable. This has never happened before.
So we have time for a few questions. If you raise your hand, we'll get a mic to you.
Yeah.
I'm
Do you want to handle the questions?
Yeah, I'll start in the back.
Hello there. If you take paired particles and separate them and do the instantaneous reversal of the spin and the other one changes all at the same time, can you superheat and supercool one of those and see if that changes it? Or does that superheating and supercooling change it to where you're changing the spin? Anyway, while I'm looking at, does the heating and the cooling change any of that instant pairing that changes? And the other thing then I'm looking at in relationship to what that implies about time, what happens if you start looking at wanting to change what you look at absolute zero, the Big Bang saying that's the beginning, and stop thinking that way? Can you substitute infinity and start looking at it as being perpetual as opposed to a beginning, end, or absolutes?
Yeah, well, that's a lot of questions, and I'm not sure I have any answers to any of those questions. But let me just ask for a clarification on the first question. Are you talking about two particles that are entangled? Is that what you mean? That are quantum entangled, or?
You do one thing to one particle, and instantaneously the other particle changes, and it implies there's some kind of pairing, which also defies time a little bit, because no matter how far you separate them, it still happens.
Right, so let me give, for the rest of you, a little bit of a background about what this question means. There is a process, or I should say a phenomenon in quantum mechanics where you can have two particles that have been prepared together so that their properties are correlated, and then you separate them. And let's say, for example, that these are spinning particles, and one of them is spinning up and one of them is spinning down, and then you separate them. Now, you can separate them in a way that you don't know whether the particle that goes that way is up or down, and you don't know whether the particle that goes that way is up or down. And there's no way of knowing until you measure it, whether it's up or down. But as soon as you do, you know that the other one's the opposite. And that seems absolutely incredible, even if they are separated by light years. And this is why this is such a remarkable phenomenon. Now, but the thing that you do to the particles is measure. Okay? So if you measure it, then you immediately know what a measurement on the other particle will do. If you do something else to the particle to disturb its property before you measure it, like cool it, then it's going to mess everything up. And this property of entanglement will be destroyed. So if you only did cooling on one of them, for example, then that is basically going to destroy the correlation that is inherent in that entanglement.
Gordon Apple. I used to work at Bell Telephone Laboratories at Homedale, so I understand what you're saying about the institutions. And what's
Yeah.
happened. I had a question for you. At these low temperatures, have you achieved a Bose-Einstein condensate, and is that something that in itself that will help this process?
Yeah. Okay, so let me say what a Bose-Einstein condensate is. Back in about 1923-24, Einstein made the following prediction. He said, get a gas of atoms of a particular kind, what we call bosons. It turns out lots and lots of atoms are bosons. Cesium-133, sodium-23, rubidium-87. These are all bosons, okay? Many, many common atoms are bosons. He said, get such a gas, make it cold enough and dense enough, and something astounding is going to happen. A large fraction of the atoms in that gas will simply stop moving. Now, they don't ever stop moving because of Heisenberg's uncertainty principle, but 1923 was before Heisenberg's uncertainty principle, so Einstein didn't know about that, never liked it anyway. But that's a different story. So they stop as much as they can. And a few years later, Einstein thought, well, that's a crazy idea. How could that possibly happen? And he said it must be a mistake. It's not a mistake. And in 1995, a group of NIST scientists, US government employees in Boulder, Colorado, made the first atomic gas Bose-Einstein condensate. And now people all over the world, including in our laboratory, are making Bose-Einstein condensates. And we have started a program with the support of NASA to send Bose-Einstein condensates into the International Space Station because the atoms are moving so slowly that they really present the best possible opportunity for making measurements because they just are going so slowly. But, you see, the problem is, you've got something going really, really slowly, but if it's on Earth, it drops, and you don't get a chance to look at it for very long. But in the space station, in microgravity, you let it go, and it just sits there. And so we got this program funded by NASA, but the program's been terminated because NASA has gone off in other directions. So we're not sure whether maybe this will get revived, but we do have hopes that we will be able to make good measurements using Bose-Einstein condensates. And we have other ideas for using Bose condensates on the ground. In fact, I'm going to a conference shortly after I finish this trip. I'm going to a conference, an international conference in Italy, where we're going to talk about what the opportunities are for doing just that.
Any questions from Joy behind you? Behind you.
Yes, Sherry Curry. I couldn't help thinking about Arnold Schwarzenegger as Dr. Freeze and one of the Batmans as you were up there. And I just wondered if this looks to me like it could be a really awesome weapon, and does it have any implications, maybe for good implications, like maybe global warming or medical procedures and that sort of thing?
Yeah, well, actually, it's this sort of stuff isn't much of a weapon. I mean, you know, this isn't the way you make ordnance by putting liquid nitrogen into plastic bottles. It does have military applications in the following sense. If we make the global positioning system was put together for military purposes, and it's still used that way for a lot of the applications. I mean, if you're driving a Jeep through the desert, the only way you're going to find your way to your destination is by some kind of a navigation system, and the global positioning system is one of the best ways of doing that. And the global positioning system can guide weapons, but it doesn't make, you know, atomic clocks don't make weapons and laser cooling don't make weapons. But there are medical applications. So for example, one of the things that we learned about in manipulating atoms was that we could grab a hold of an atom with a laser beam and move it around. Well, it turns out you can do exactly the same thing for pretty much the same reason to larger objects, things as big as a living cell. So we have done experiments in our laboratory where we take living cells and then we take viruses that would normally attack those living cells. And by holding on to the living cell and holding on to the viruses, we can study the way in which the virus attaches itself to the cell wall. Now, that initial attachment is the first step in infection. And the idea there was to see what kinds of chemical barriers could be introduced to prevent the virus from attaching itself to the cell wall. And it turned out that the classical ways of doing this, the usual ways that people had been doing for measuring these kinds of things, didn't work for the most effective chemicals that would interrupt this process. Those usual techniques didn't work, and we had to use these techniques where we could take just a single cell and a single virus-coated microsphere, as it turned out, and do those experiments with that single cell in a very low concentration of this incredibly effective chemical inhibitor. And we were able to show which of a number of candidates were the most effective inhibitors for doing this sort of thing. Well, applications of this are still a long way off, but it's the kind of thing that really has a lot of promise for doing something about infection in a very different way from the kinds of things that we do today.
One more question, and it's over there.
Research comparing Europe and Asia with the United States. And in addition to investor behavior, investors in the U.S. looking for short-term returns as opposed to the Europeans and the Asians, are there specific policies of their governments that encourage private sector funding for basic research?
That's a good question. I don't know. I mean, I'm a physicist. What do I know? But that would be an interesting thing to ask about. I really don't know whether other countries have private sector investment. I do know that a lot of countries have a lot of public sector investment. You know, Singapore is pouring huge amounts of money into certain sectors of scientific research and attracting scientists from all over Europe to go to Singapore, and Europe has pretty good funding. So they're being very effective. But I don't know about the private sector. Good question.
Let's thank Dr. Phillips for coming today.
Thank you. Thanks very much.
Thank you all for coming, and we'll see you at the next one.